appreciated the great introductions, and all of us, I think, both the students and the lecturers are happy to be introduced to this very nice and forward-looking facility. This lecture series was scheduled 3 years ago, and we've waited 2 years to get by the pandemic in order to have the lectures. In some ways, the field's moved forward, so you'll hear more recent results and ideas of this field. This is a very young field, and it covers a very broad part of physics, from the very deepest theory, starting with Einstein's theory of general relativity, to some very, very practical, technical problems that are inherent in being able to detect gravitational waves. So the breadth of the field is really astounding, and you need all that to be able to pull together and do the science. So I think you'll see that we've tried to cover that with the kind of lectures that we have that'll go from the very practical problems that we have technically and experimentally to the phenomenology and the theory that we need to interpret the data, to the way we have to take and analyze gravitational wave data. In addition to that, we're going to try to introduce you to the future. That is, the ideas for doing this in your careers in the coming years that maybe move on from these first detectors that we have, including how to do it in space and how that complements what we're doing on the Earth's surface. So it's going to be a very broad array of lectures that we'll give you. I'll try to give you just a sense of who we are first, so that part of the real value of coming to a school like this, I know, having been in many of these, is the interactions that you can have that can be lasting, learning about each other, but also with the lecturers. So you've got a chance over a week to meet us, and some of us aren't going to lecture until later in the week, so I want to at least flash a quick view of who we are, so that you don't just have to stare at the name tags to see them. So I'm going to give you kind of, as soon as I finish this little introduction, kind of broad oversweep of the field, just to introduce it. We'll start then with Alessandra Bonanno from the Max Planck Society, and I've got a picture of her here, and she'll give basically theory and phenomenology, interpretation of data, what we really need to be able to understand gravitational wave data. And I would say this will begin with a somewhat theoretical beginning. Don't be scared off, because as I say, you need that to kind of move on, and she will also show you some results and how they rely on this kind of theoretical abilities that she'll talk about. Just to quickly introduce the other lecturers, we'll have Lisa Barsotti, who will talk about the actual detectors themselves, the LIGO and the Virgo, somewhat the Virgo detector. Patrick Sutton, they're all sitting over in here, by the way, but at least you've seen one picture. Patrick sent me a better picture of himself today, but I didn't have time to put it on. Eric Castavanides, our historically, someone who actually is Greek, who's here and teaching and working in gravitational waves. And I'm going to give a public lecture. Eric will give 2 lectures, as most will. And in space, we have a lecture from Stefano Vitali, who chose to send me a picture of the group that's working on how to build a gravitational wave experiment in space. It's actually approved and funded for the first stages and planned to be launched in the mid-2030s. You'll hear something about that from Stefano. The next lecturers we have are Jan Harms and Marika Brancesi. Unfortunately, they've both contracted COVID in the last 3 or 4 days. So they will be talking probably by Zoom. America actually got COVID last Wednesday. If she tests negative this Wednesday, she still may come and give them in person, and they're married to each other. And Jan just got it. I just learned as I arrived at the airport here, so we'll have to do without that. Matt Evans, who's over here somewhere, who will talk about the future ideas for next generation gravitational wave detector. And I've talked about America and Patrick Sutton. We're going to try to end the last day, by the time we get to the last day, concentrating on the future. So that's the plan. And now I'll give you kind of a brief story, if you want, of gravitational waves before we have Alessandra start on the actual courses themselves. So the story starts really 1.3 billion years ago. And at that time, just to put it in perspective, here on Earth, we were just changing from single cell to multi-cell life. And so that's kind of where it started. At that time, in the distant universe, 2 black holes decided to come together. Let me just remind you what a black hole is, just in general, with the kind of black holes we talk about. It's regions of space that are created by super dense matter from where nothing can escape, including light, because of the strength of gravity. So it's a place that's mathematically unable to, and nothing's able to escape. Some of these may form when there's very large stars that collapse and die, and that's primarily the expected source of most of what we've observed, but not proven. There's other possibilities of what, and some difficulties with that interpretation even that you'll hear over the coming days. If they come from the collapse of a heavy star, and then these black holes merge together in what we see, they should be somewhere between 3 and 100 times the mass of our sun. 3 is roughly the minimum mass in order to have enough gravitational strength to be a black hole. And for other reasons, the maximum is thought to be not more than about 100. Of course, there's a totally different scale black hole that's at the center of our universe. Okay. The picture that I showed you of 2 black holes merging 1.3 million years ago was a snapshot. And if I put that snapshot on a picture on the map of Crete at the moment that I captured the snapshot, then the 2 black holes would be more or less the size of this island. One of them that we detected, we'll show you how we know, was about 36 times the mass of our sun. The other one, 29 times the mass of our sun. And by the time that picture is taken, they're going around each other at relativistic speeds, at about half the speed of light. So you have to imagine what's really happening on the scale that we're talking about, each of these 36 times the mass of our sun concentrated in such a small space. This is an early video that was made after this first detection was made. So we started with the picture that we saw, and now I'm showing you the time evolution of the merger itself using the theory, general relativistic theory, to be the background of these calculations of what happens in this merger. You can see them gravitationally come together, merge, and then oscillate a little bit afterwards. We'll see in detail what that looks like in terms of equations, in terms of pictorially and graphs and so forth as we go along, but that's at least a visual concept. When they come together, they then started 1.3 billion years ago and radiated away gravitational waves. Now, gravitational waves, of course, most of us expect or look, or first time we hear of it, think of it like electromagnetic waves. But in our best understanding now in general relativity, there are actually distortions in space-time itself. There's nothing that we've seen. We'll show you how well we know. Like the photon that's a propagator, it's a distortion in space and time itself. As it goes through and distorts space and time, exaggerated by a little bit in that picture, it distorts things at the Earth. We build a detector called an interferometer, which you'll hear a lot about. The size of the interferometer has to do with us trying to grapple with how small the effect is, and you'll see how easy it is or hard it is to make this big. This picture here shows the LIGO interferometer in Washington, Hanford, Washington, and each arm is 4 kilometers, and they're perpendicular to each other. Now, as we continue, this came to the Earth on September 14th, 2015. It entered the southern hemisphere. We know from the shapes and time of the observed signals that it more or less came through the indicated places that are shown here. And then it was detected in Livingston, Louisiana. This is the data with only what we call whitening of the data, nothing done basically to do a lot of data analysis. It's the data that comes out of a time frequency series. What's shown is the strain. I'll show you what the strain means in a minute, but it's technically what we measure if there's a distortion of space and time. The units of it, which I show here, are really important in almost everything you're going to hear this week, because it's what makes the problem so difficult. It's 10 to the minus 21. So we're measuring something as small as 10 to the minus 21. The time scale is shown here for the very first event is about 0.2 of 1 second. So the gravitational wave, you're seeing the time evolution of it when it enters our frequency band, which is the audio band, basically. We don't do audio, but where the Earth is quiet is where we've learned by evolution to communicate with each other. And that's more or less the band that's available if you work on the Earth's surface. If you want a different frequency band, then you go to space, and we'll talk about that during the week. So this was detected in Livingston, Louisiana, and then 6.7 or 7 milliseconds later, something that looks almost identical was detected in Hanford, Washington. The fact that they gave the same signal, 7 milliseconds difference in time, helped tell where it was in pointing. The fact that two signals look so much alike is a lot of what gave us confidence, or gives us confidence, when we detect gravitational waves. I've superposed on it the gravitational wave prediction, and from Einstein's theory of general relativity, and you can see, we'll go certainly in the next talk, you'll learn a lot more about that. But the fact that it looks so much like the data is what gave such early confidence that based on one single observation, we had detected something that was interpreted as gravitational waves from the merger of two black holes. That's unusual in physics. In my lifetime in physics and physics that I know, I can only think of one other major discovery that happened by observing a single event, and that was the omega minus, the final observed baryon that proved that, let's say, gave us confidence that the quark model of Murray-Gell-Mann was the correct description of particles at a sub level of quarks. But usually it takes a lot more data, so this is an unusual kind of observation. Now let's reflect back on it just a little bit. You'll hear this in much more quantitatively in the next lecture. Starting from Newton's theory, which is really the most successful theory of physics, I think, ever, was written in the Principia, his big volume, in 1687. And he wrote down and derived that the fact that if you have two masses, then the force of attraction between them is the product of the masses of the two objects divided by the square of how far apart they are times a constant. He couldn't determine the constant. In fact, it took another 100 years to determine what the constant was. But that formula basically described everything that we knew about or found out or had about gravity almost up till the time of Einstein in the early 1900s. So over 200 years, whether you talk about the moon going around the Earth or the Earth around the sun or astronomical observations or the tides or jumping up and down, it doesn't matter. It's universal, and that's why Newton called it a universal theory of gravity. By the time of Einstein, there was only one discrepancy that had been observed from this theory of Newton's, and that was the orbit of Mercury around the sun. The orbit of Mercury around the sun is very, very elliptical, and it processes forward a calculable amount due to the positions of all the planets and moons and so forth gravitationally as it comes past the sun each time around. And the actual observations were somewhat different by about 10% from Newton's theory. And that was the only discrepancy that we had from Newton's theory of gravity by the time Einstein came along. As had been discovered earlier with the planet Neptune and Uranus's orbit, it could mean that there was something we hadn't seen yet. And so there were predictions that there was some mass of some sort or masses between Mercury and the sun that could account for this difference. So it isn't like this was a terrible, terrible catastrophe at the time. Of course, by now, we've searched even with NASA satellites for objects between Mercury and the sun, and down to the scales of even tens of kilometers, nothing's been observed. So this was the only puzzle that existed at the time of Einstein. Einstein then gave us a new theory of gravity in 1915. And when he gave the new theory of gravity, he immediately showed that it got the right answer for Mercury around the sun. So his very initial lecture, he was certainly aware of that discrepancy and that it gave the right time. This theory, of course, is based on space and time being unified into a four-dimensional space-time, which you'll hear about somewhat in the coming lectures. Physically, what it does is warps space and time, or changes the space and time. The presence of a mass changes the structure of space and time around it. And as you can see in this picture, the presence of the sun and the earth, the sun then warps space and time. Each point on this is changed in both the spatial dimensions, the three spatial dimensions, but also in time, which I can't, of course, show in here. So every point is changed in space and time. And of course, if you think of this structure down here, or something like a trampoline, when you put something heavy on it, goes down like that, that's what then is the distortion pictorially that attracts the sun, the earth to the sun, and then the centripetal force pushes outward, and the equilibrium is the orbit that it has around the sun. Fixing a problem which maybe most people wouldn't think was maybe the biggest problem in the world, that is the orbit of Mercury, is certainly not enough for us to throw away a more than 200-year-old theory that was as profound as Newton's theory was. So Einstein made a second important prediction, and the prediction was that due to the fact that we have a distortion in space-time, if you go through a region of space where space and time is distorted, it doesn't matter whether I have a massive body like the Earth near the sun or a massless body like a photon, when it passes through that distorted region, its orbit will be changed. And so what Einstein predicted or calculated was that if we looked at a star that was behind our sun, when it went behind the sun, if we could see it, it would distort as it came near the sun. You could observe that if you happen to try to look at the sun at exactly the time of a full eclipse. So he predicted that in a full eclipse, you could see the distortion of the orbit as it went around the sun. That was done by Arthur Eddington in 1919, and that was at least the proof that the new theory of gravity not only fixed a problem that existed in Newton's theory, but predicted the bending of light. Of course, the bending of light now is used quite commonly in astronomy to study objects as actually a tool, which often happens in physics. To go on to the subject of these lectures, the next year after Einstein brought out his theory of general relativity, he wrote a little paper which basically predicted gravitational waves. And that paper was published in 1916. It's a very short paper. It actually has some errors in it. But basically, he didn't derive gravitational waves at that point, but rather by noticing in fact, it also has an error of a factor of 2 in it, which would have been important in our measurements if he hadn't found it. But in this prediction of gravitational waves, this was done by basically a phenomenological leap. He noticed that formulated a particular way, the equations of general relativity looked like the equations of electricity and magnetism, somewhat the form. And therefore, since electricity and magnetism have waves, by analogy, he predicted that gravitational waves would have waves. And so that was kind of an insight rather than a fundamental derivation. He came back to try to derive it in the 1930s, but didn't actually derive it in the 1930s. And in fact, it remained somewhat controversial until the 1950s because of the fact that people couldn't derive it from the basic theory, and it's usually thought that the turning point, the point where people actually believed that gravitational waves existed theoretically, was a conference held in Chapel Hill, North Carolina in 1957. So it's 40 years after the first predictions of Einstein. At that point, about 40 theoretical physicists came together to try to grapple with the problem of whether gravitational waves could be derived from the fundamental theory of general relativity. And in fact, at that conference, the first person I named there, Pirani, gave a very elegant derivation of gravitational waves from the theory, and variants of that have been used. At that same conference, Richard Feynman was at the same conference, and at that conference, Richard Feynman did what he does, or what he did, which is to say that in addition to proving that gravitational waves come out of the general theory, that if there are gravitational waves, then they must be able to do something. And in his case, he said they must be able to transfer energy. So could gravitational waves transfer energy? He grappled with that question in a kind of phenomenological way. He made a picture of what he called a sticky bead argument. That argument was you have a bar like the bar that I show here and a couple rings around it. If a gravitational wave goes through it, it distorts the bar in such a way that the bar gets fatter, part of it, and narrower and fatter at the frequency of the gravitational wave. And and if the beads move, that means that there's something made them move, and that was friction between the bar, and that friction is heat. Heat is energy, so there was a transfer of energy. So this was basically the sticky bead argument that Feynman gave. At that meeting was an experimentalist named Weber, who basically, I think, grabbed this idea and made the first detectors later that tried to detect gravitational waves, and were the main way. I don't think anybody's going to really talk about it in the talks here, but it was the main way people searched for gravitational waves until almost 2000 or something like the year 2000. And so bars were basically an element that, instead of having rings around it, were detectors that measured the distortion of a bar. So gravitational waves then have to come from some source. We learned in 1918 that in the second paper that Einstein wrote on gravitational waves, that in contrast to electromagnetism, where the source is a binary source like Hertz used to prove electromagnetism, it's a quadrupole. And so the force has to be a quadrupole change of matter and acceleration. So basically, the example there's different examples, of course, but the example that's most relevant to our observations is two objects going around each other like shown here, and they will radiate away by gravitational wave energy in the form of gravitational waves that propagate through space at the speed of light. And that's the then prediction of Einstein's equations. You can write down general relativity in a lot of different ways. I just happen to do it this way to show that it looks like the electromagnetic equations. The equation here, the little h, is the thing you'll hear about this week, which is what we measure. It's called the strain, h mu nu. But the equation looks like the same equation as electromagnetism, where we have plane waves. So you expect to have plane waves that come out. And the only difference being, as you can see in the picture here, that the waves are at 45 degrees from each other instead of 90 degrees from each other. And that's basically, in a sense, a reflection of the fact that gravity is a spin tube. Let me show you something that you won't see, so we'll probably in the lectures, which is why we can't do gravitational waves like the Hertz experiment. The Hertz experiment was beautiful for electromagnetism. We had the equations. This experiment was done where he created a binary source, a source of oscillating charges, went in the next room, detected them, moved forward and backward, and saw electromagnetic waves. So what if we tried to do that for gravitational waves? I've done here just an example. If we took the binary system that I talk about, imagine a bar that's a meter or so long and 1,000-kilometer weight on each side, and you spin it, say 1,000 hertz. Better get out of the room. It's not very safe. And go some distance away. You want to go a distance where you can see the waves, but I've purposely picked a shorter distance here, 300 meters. If you go 300 meters away and calculate the gravitational wave strength that you get, it's a number of that little h that's 10 to the minus 35. You'll see this week that we try to measure how hard it is, but we're successful in measuring something that's 10 to the minus 21. So in order to make a man-made source, as we would make it kind of classically, we're 13 or 14 orders of magnitude away from being able to do that. So instead, which at least when I was a student in experimental physics, I was always warned that you should always have everything under your control when you do an experiment. We don't have that luxury in this case because we can't create a source that's strong enough. So we're forced to rely on nature to create a source for us. And then we're very fortunate and lucky that the sources that we create are so interesting themselves, the sources that give the gravitational waves. So it kind of works both ways. Anyway, the effects of gravitational waves, of course, are very small, but if you take the one that we detected, it's approximately 10 to the minus 21 when you take and do the same kind of calculation that I just did before. So we're basically in the regime where we're going to use nature, which means the universe for us, to create gravitational waves that we can detect. Almost everything you'll hear this week is on the first, and the pictures that I showed, source of gravitational waves. That is a binary system that's in-spiraling, as the picture that I showed was. The first example that we detected was black hole. We also have detected neutron star, and neutron star black hole. There may be other sources that we don't know or anticipate, but that's basically everything that's been detected so far in gravitational waves, and certainly far from the whole story of what we expect in the future and hope we can detect with gravitational waves. So I list some other sources that are kind of not today's sources, but hopefully in the future. First one would be the collapse of a star, a supernova, maybe related to gamma ray burst, something that a supernova will give during the collapse a gravitational signal. When it merges together, the neutrinos are sent out, and so you can detect neutrinos. And finally, there's the detections that we are used to for supernova, the shock wave that gives electromagnetic signals. So to really understand a supernova, you'd like to have all three. If we have a supernova somewhere near enough to our galaxy in the future, we would expect to see a burst signal that could be seen both in gravitational waves, hopefully with neutrinos, and with electromagnetic waves, and then we could understand the collapse science much better than we do today. Another example of a burst-type signal is a gamma ray burst, which we'll talk about some when we talk about the neutron-star mergers. Another example quite different from the two that I said, because both the two that I talked about, almost everything that we talk about now or do, are transient signals. A signal that comes, then it's gone, is a periodic signal. So what kind of periodic signal might there be? The primary example that we have and look for is pulsars in our own galaxy, pulsar systems in our own galaxy. And if we can see a pulsar system in our own galaxy, we have the advantage then that it means that a spinning pulsar has a quadrupole moment somehow, and by not being perfectly spherically symmetrical. And if it gives a signal, then we have the advantage experimentally that we can continue to study that object in the future. The transient ones that we're studying now come and go. We have to study a new one when we experimentally. The last source, which I shouldn't ignore, is the fact that someday we hope that it would be possible, not with present-day detectors, to detect the stochastic background from the very early universe. And I think we all know that trying to understand the very early universe is both puzzling and very difficult. We have what happened at the very beginning, in the first few minutes. We have the problem of inflation, which we don't understand. And the best tool we have is studying the cosmic microwave background signals. And the cosmic microwave background is limited by the fact that the photons are absorbed at early times, and the universe is opaque before a few 100,000 years after the Big Bang. So right now, using other probes, we can only go back to a few 100,000 years after the Big Bang. If we could detect neutrinos from the Big Bang, we could go back to a few seconds after the Big Bang. And if we can detect neutrinos, we go back to the very earliest moments of the Big Bang. So this is all kind of the future, very, very long range that might be seen of sources that we know something about. Also, we have to keep in mind that the universe only has a small fraction that's known matter, and we don't know really what the rest is, dark matter and dark energy. And so there's plenty of room for sources that don't have anything to do with normal matter. And it's another thing that we look for in our signals now is look for what we call unmodeled sources, and I think you'll hear about that in the talks this week. So unmodeled sources is how do you look for something that may be new and you don't have the knowledge of what they are, and there's no electromagnetic counterpart necessarily. So the signal for compact binary collisions, which is most of what we'll study, has more or less three stages. This is a little picture that was drawn by Kip Thorne years ago. And the left part just shows the in spiral, which is the getting higher frequency and higher amplitude in little h as it merges closer and closer and gets faster and faster. The merger itself are the coalescence, and the merger itself is basically maybe potentially the most interesting part physically because it's in the regime of strong field gravitation. And then finally the system has to settle down, and there's the physics of the ring down itself. You'll hear much about this before. I'm just kind of giving you a picture. On the right side is a picture then of the difference between light objects, light binary systems, and a heavier binary system. You'll see the bottom one just has a few wiggles, and that's because the detectors that we have only go down to 10 hertz or tens of hertz, and so we can only see frequencies above that. And if the objects are heavy enough, then they don't ever get to that frequency. The very first one we saw was barely heavy enough. And so we only saw half a dozen or so oscillations, and ones later, as you'll see, have many more. And then in lighter objects like neutron star mergers, then we see thousands of oscillations. So just a few words about what's the way you go about detecting them. You're going to hear a lot about this technically. But imagine that you just had a ring of free masses, and you made a ring of free masses, and then a gravitational wave goes through it. We talked about the fact that objects, if we're talking about the kind of objects we've detected, the size of that effect is little h of 10 to the minus 21. So in that case, delta L equals h times L. And so the challenge then is to measure a change in how circular this series of free masses is to 1 part in 10 to the 21. That's a very difficult number, and that's why we make the detectors kilometers long instead of meters in size. And that means we only have the difficult problem of trying to measure 10 to the minus 18 meters, not 10 to the minus 21 meter delta change in length. You'll hear a lot of technical details, but in the simplest form, I would characterize the experimental challenges as two. One is how do you do interferometry well enough so that you can see the difference in arrival time between light going down one arm and a perpendicular arm and coming back, which would be in time unless a gravitational wave makes the path longer in one arm and shorter in the other. The accuracy that we need in order to get the 10 to the minus 18 meters is 1 part in 10 to the 12th. What that means is that when the light goes down one arm and the other arm, we have to be able to detect a change in phase of 1 part in 10 to the 12th. Typically, interferometers that you would use in a university laboratory for physics students is maybe 1 part in 100, or 1 part, something like that, where you see the fringes. Technical interferometers that are somewhat better are better by a few orders of magnitude than that, but we're talking about way beyond the kind of interferometry that's ever been done in any other technical instrument. And that takes an enormous number of innovations in how to do interferometry itself. And you'll hear some discussion of that, both in what we do now and how we do better in the future. A second problem, these are not the only problems, but I'd say they're the most headlined problems. The second problem is that as much as it seems like we live on a pretty stable Earth, it's vibrating all the time. And it vibrates at the frequencies that we work at, but it basically has a region where it is pretty free, is freest of vibration. That starts at about 10 hertz and goes up to about 10,000 hertz. At 10 below 10 hertz, the Earth shakes like crazy. And our ears have basically adapted to that, and we basically hear and talk to each other in the audio band. We have nothing to do with audio in gravitational waves, but basically the same band is where the Earth itself is the quietest in terms of moving around. And so that's the band we work in. Nevertheless, even in that band, the shaking of the Earth is far beyond what we can tolerate if we just try to connect to the Earth itself. So in general, if you go into a undergraduate physics lab, you have an optical table and you put the mirrors down and put them down. We can't do that. Instead, we can't do that because the Earth just moves too much. Instead, we have to make sure that our mirrors are basically isolated from the Earth's. So the interferometers that you'll hear about are what we call suspended mass interferometers. The masses are basically made to be independent of the motions of the Earth. And I won't go into the technology of that, but that's been the second, I think, really big challenge, and the one that mattered the most in making the early detections. So then the vibrations I'm showing at 1 or 2 times a second cause the time it takes for light to go down the two arms to come back slightly differently, and then we see a signal. I'm going to skip this just because of time. What we've built for LIGO in the U.S. is 2 identical detectors. What I show here is a map of the U.S. They're 3,000 kilometers apart, 3,002. At the speed of light, that's 10 milliseconds to go from one to the other. One's in the state of Washington on high desert, and the other is in Livingston, Louisiana, a kind of forest area where they cut down pine trees to make paper. And they're 3,000 kilometers apart. What that means is that light, a gravitational wave that comes through here first would be detected here 10 milliseconds later, or vice versa. The event that I showed you was 7 milliseconds difference, or 6.7 milliseconds difference. And we require then that the two be together within this plus or minus 10 millisecond band, and in fact use the out of time period bands to understand what the natural, any backgrounds that we have, our ability to do detections. So our ability to see something depends on it seeing it in time, as I show here, and you'll hear more about that. This is a picture of the beginning of LIGO when we first did the construction in 1994 and had a big debate. And that debate was the following, that this is shown here, and we are fixed in Louisiana because of the land that we got. But in Washington, where we're in high desert, we're on a big plateau of desert that's owned by the government, the Atomic Energy Commission, Department of Energy now. And we could orient it any way we want. So how do you orient the two interferometers with respect to each other? Why was there a debate? The reason that there's a debate is you have to trade off kind of confidence that we detected gravitational waves, I'll explain what I mean in a minute, versus more information. So if you have a detected gravitational wave and the one interferometer is 45 degrees from the other one, we get more information because we can use it to tell the two components, which I showed very quickly on an earlier slide, of the gravitational waves, just like you have two components in electromagnetic waves. If they're parallel to each other, the signals should look alike. They can't quite be parallel because of the curvature of the Earth, but we decided to make them parallel to the 16-degree curvature of the Earth on top of each other. Our reason was simple. It was because gravitational waves had never been detected, and we wanted as much confidence as possible when we made the first detections that we had detected gravitational waves. That's happened now. We have two detectors that aren't capable of decoupling the two components of the gravitational waves, like the two components of electromagnetic waves. The third detector is now operational in Italy, the Virgo detector, but the combination of the three aren't yet good enough to decompose the two components of the gravitational waves. Maybe one of our lectures will talk about that as we go along. Just a picture that there's a lot of big hardware that goes into the gravitational waves, the biggest being the big long beam pipes that have to be at high vacuum. And so those you'll hear about. This is just the tanks that they go in and the optics that are there. I'll skip them because of time, and the laser, so that's just the equipment. The interferometer scheme itself I'm going to skip, but starting from the simple interferometer down to one where you can do interferometry at the level of telling a phase change of 1 part in 10 to the 12th has a lot of sophistication and tricks, and you'll hear a little bit about that this week, or the challenges. What limits the interferometer? It's worth me spending just a few seconds on that. There are a lot of things that limit it from just the picture of an ideal detector. First, no matter how much we pump on the vacuum, we have residual molecules, so we have scattering off gas in the arms. That scattering can create a trajectory that then bounces off the walls, takes more time to get back, and it's no longer the shortest path. So that's one background we have to worry about. Of course, we try to deal with that by making a good enough vacuum. The laser itself has very strict requirements. It has to be stable in wavelength, in amplitude, in pointing, and so it takes a very special laser. The test masses themselves have seismic noise from shaking, and that no matter what we do, we hang them and try to isolate them from the Earth, but at some level that comes through. Another issue is that the test masses themselves are at room temperature in the present generation of detectors, and so they have thermal or Brownian motion and Brownian noise. Finally, if we get good enough, we get down to where there's quantum effects that limit the interferometer as we increase the light levels. The pressure on we get better statistics, better shot noise, but the pressure on the mirrors is a counterbalance, and that gives a limitation. So when that's all put together, we get a shape for where the sensitivity will be. And you recall I said we were from more or less 10 hertz to 10,000 hertz. The shaded region is then where we're sensitive in the present generation of detectors. On the left-hand scale is the sensitivity, and all those lines are the different lines for the different backgrounds. In the present generation, more or less, we're limited at the lowest frequencies, if you look at the shaded region, by seismic effects. That's the residual shaking of the Earth. You can see it's very, very steep. So it drops like something like frequency to the 4th power. And because it's very steep, it's not the problem when we go to higher frequencies. But at the lowest frequencies, it's the limitation. And for these black hole merger events, the main thing that we've detected, that is the limiting factor, is how well we handle the seismic background. At the highest frequencies, we're limited by basically how many photons we have. photostatistics, or what's called shot noise, and that is at the higher frequencies. At the middle frequencies, we're limited by these thermal effects that I talked about, thermal noise. And so this is not an ideal situation experimentally. Usually an experiment that you do is limited by something and you work on that. In our case, there's an array of 3 different basic ones, and then other effects lurking below as we improve the detector. So the technical challenges as we move on and make better detectors have more than just solving maybe a simple problem involved. When we built LIGO, it worked well enough that we were soon better than these bars had been, but not sensitive enough to detect gravitational waves. And we periodically would take data for 6 months to a year, learn from the data from the data and from tests what limited the interferometer, and then fix it and then run again. So this is more or less 1 year, roughly 1 year periods. You run for a year, you improve it for a year, you run for a year, you improve it for a year. This is very different than is done in most other experiments. I came out of particle physics, and if you work at CERN on a particle physics experiment, you want to run all the time if you can and take as little time off as possible, because most of the physics is limited by statistics. We're limited by sensitivity. It's something different. And in our case, we measure an amplitude. Whoops. I touched this. I don't know. There it goes. We measure an amplitude, not a power, and that means that if we make it twice as sensitive, we see twice as far out in the universe. If we see twice as far out, we get 8 times as much volume of universe to look at, and so the rate goes up very quickly with an increase in sensitivity. So in our case, there's a big motivation to improve sensitivity, even a small amount, because you gain so quickly. So the ratio of how much time we spend improving the detector versus how much time we take taking the data, this is a question I'm always asked by people, is quite different than, say, for particle physics. And at present, we were down because of the pandemic, but we're down for a period of several years before we run again next year. This is just to mention the one, since I mentioned it before, the one problem of how do we isolate ourselves from the ground. It's actually simple technologies. We use a combination of shock absorbers like you have in your car, a little fancier, but like you have in your car, 4 layers of them. And that wasn't good enough. That got us to maybe 10 to the minus 10. And coupled with that, then we did something that's harder, which is put seismometers buried into the detector, detected the residual motion, and pushed back against it. So we have what we call active seismic isolation. You'll probably hear more about this as the week goes on. As we finally made a big step in improvement, we made the first detections. And I'm going to skip because you'll hear most of this, and time is moving on. So in order to search, I just want to mention we do something you'll hear about, I think even in the next lecture, match filtering. Match filtering means that we try to match what we see in the shape and the data with calculated waveforms that would come from known objects. So the picture here in the lower left is a picture of hundreds of thousands of calculated waveforms covering the region that we can cover from about 100 solar masses and the frequencies from 10 to thousands of hertz. This gives hundreds of thousands of templates, which, as I say, you'll hear about and have to be good. And we compare that with each piece of data. So the data, which has no triggering, it basically is the time frequency data, is compared with that. and we see a signal. We do it by what we call match filtering, where you multiply the expected waveform times the noise and can pick up the signal, but I'll skip that. This is the second event that was ever seen, and it shows that by lighter masses, and the only reason I show it is by lighter masses, you see many, many, many more wiggles. This was lighter, so it really didn't have as good a signal to noise in terms of detecting it, but was better for other things. For example, this event, because it had so many wiggles, could be used to test general relativity better than the first event itself. I'm going to move on. We have, this is just a simple one, but I just want to mention it. We have tried to see if there's any deviation in the waves that would indicate there's anything equivalent. There's not in Einstein's equations, obviously, but anything equivalent of the photon, what people might call the graviton, or some other shape. This is just a picture of where we put in a dispersion term. If you put in a dispersion term in a limit, that's putting in a small mass for a massive object that's with it. A small mass will make it make the waveform somewhat different, and you can test for that. And so with that, we're able to put a mass limit on the graviton. I didn't update that to the best mass limits we have. And we've detected now a lot of events, which you'll see, and I'm going to skip. Now let me just show one other thing, I think, because I don't want to go too long today. By 2017, we made the first detection in 2015. The detector in Italy was working well enough to join us. And by joining us, we could do a much better job of telling the direction something came from in the sky. With two detectors in the US, we could basically see a stripe that would go around the Earth. By looking at the waveforms a little bit, we get the time of arrival, we could actually locate that somewhat. So the first figure that I showed on the very early plot is kind of a band for a while. But the resolution that we got in LIGO itself was about 1,000 square degrees. Adding the Virgo detector brings that down to tens of square degrees. It depends on the event itself and where it is. And that starts to be good enough so that what we see is in a field that you could use for comparing whether astronomical observations are made. And so adding the Virgo detector, the huge difference for us is that we, with 3 detectors, can triangulate. Soon after that, we observed an event, which is shown here, and it'll be talked about a lot, I think, so I'm not going to dwell on it. I'm going to show just a couple things. We're having the better resolution. That one was 31 square degrees with the 3 of them. It was also seen in high energy gamma rays in that same band. I'll show you that in a second. Also note on this, the picture in the middle, which I highlighted, this is the time frequency plot, the real event, and on top of it is this thing here, which is what we call a glitch, a typical experimental problem where there's noise in the experimental devices themselves. It's something we grapple with hard. Some of them we can understand and interpret, or otherwise treat the data. For this event, that was just cut out so that the event was there long enough. But technical phenomena in the detectors themselves have to be considered whenever you're analyzing these data. It's probably me. This is that first event seen in coincidence with electromagnetic signals. So everything I talked about so far, black holes don't give electromagnetic signals. This was 2 years or so later, and after the Virgo detector joined LIGO, and what we saw in LIGO is shown here. This is frequency, and this is time. and it's the line that comes up here. 1.7, 2 seconds later, was observed by the Fermi satellite and another satellite, a signal of high-energy gamma rays. And the high-energy gamma rays, they could tell, were within the bigger block here. So they were in the same region. This is the region of space where it was localized for gravitational waves, the region of space where it was localized for high-energy photons. And so the coincidence, we had confidence then in the coincidence. And the first thing to notice is the time difference between them is a couple seconds. That, after it's was analyzed as an object that's 150 million light years away. 150 million light years is 1.5 10 to the 15 seconds. I'm talking about 2 seconds here. So without doing anything, this is that we experimentally see here that the speed of light and the speed of gravitational waves are the same to 1 part in 10 to the 15 without any data analysis needed. You expect the signal to be later for the gamma rays because the merger itself of, this is two neutron stars, the merger itself gives the gravitational waves. The nuclear physics after the merger is what gives the gamma rays. The gravitational waves were given by the merger. So some unknown amount, but a couple seconds would be expected. That gave enough confidence to do what what we need to do to really combine gravitational wave information with electromagnetic information. We need to somehow be able to inform the electromagnetic community with confidence that we see something in gravitational waves, and then let them look and see if they see anything. So basically, schematically, what we do is to do a quick analysis of gravitational waves and the sky location and try to evaluate the event. And we have to be reasonably confident at something like 90% level, because if we tell astronomers to look and then we say, oops, later too many times, they're going to lose confidence in us. So we have to, with some reliability, be able to tell them quickly, within minutes, where to look and what we see. Of course, they want to know more about what we see than we're confident in giving them necessarily. And then we spend weeks, days, months analyzing it in great detail. But this problem of doing a very quick analysis, having confidence in it, being able to tell them enough so that they're interested in looking, is a big challenge that we deal with in our experiments. That particular observation, after it was seen in gamma rays and seen in gravitational waves, was used to alert the whole astronomical community. Roughly 2,000 astronomical instruments in the world were pointed in that direction, and it was observed in many different wavelengths, not neutrinos, which are on here, but radio waves, infrared, X-rays, and so forth. And basically, I'm going to skip that. Basically, it fits a model called a kilonova model, which may be right or not. But the kilonova model basically is a model in the literature that fit a neutron star, the physics of a neutron star merger, and has been used to analyze that data. An interesting kind of physical outcome of that is that the kilonova model gives us a perhaps better explanation of where heavy elements came from in the Earth than we previously had. It's been a puzzle since I was a student, how heavy elements like gold and platinum that we're so fond of ever got into the Earth, because the universe is made out of hydrogen and helium, and then we have a fusion process in all the stars, which creates elements up to about iron, but not the heavier ones. And so where did the heavy ones come from? People concocted various ideas using some nuclear physics, for example, called the R process, but there's never been a very good explanation. This is not necessarily the right explanation, because it's one event, but in this in this observation, in this scheme, it could explain where they came from. The future is to look, as I said, at these other kinds of sources for the ground-based events, as well as doing the coalescing binary systems better. To do the multi-messenger astronomy, we need to have coverage around the globe that's better. And we will have, in the reasonable future, a new detector in Japan, which is being made to work now, and the third LIGO detector, which is under construction, just beginning construction in India, and hopefully it'll be ready in about 2026 or so. Kagra, the Japanese one, is underground, and it's the first test of how to do an interferometer underground, and to do an interferometer that's cooled from room temperature. So in addition to having an additional detector, we are getting information on technology by what's being done there. What's anticipated, if you look at the upper left-hand plot, it's how well we can tell where something came from more or less now. And the lower right-hand is where we should be once Kagra, the Japanese detector, and the Indian detector are on, where no matter where we detect gravitational waves, we should be able to locate it well enough for astronomers. I'm going to skip talking, in order to end this, I'm going to skip talking about the next generation detectors. We're going to get nice talks on that. I'll just mention a couple things about them, what's being considered. There's two. There's one in the U.S., which looks on the Earth's surface, and one in Europe underground, both concepts, not approved, funded detectors. Again, in the long-term future, we need somehow 3 detectors of some sort in order to locate things. But there's other changes that are at least being anticipated. The European detector is being proposed to be deep underground. Deep underground naturally has less seismic vibration, and there's a lot less free land, so it can be put somewhere. There's 2 different proposals in Europe where that'll be. I'll leave that for the week. The arms can be longer. Their arms are 10 kilometers. I'll remind you, I showed you 4 kilometers. It's a triangle shape, which is also, as you'll learn, the shape that's proposed for the experiments in space. A big step is to make it cool, that is cryogenic, and you can have special configurations to make it sensitive at high frequencies or at low frequencies. The one on the Earth's surface is what we've been looking at more and will be talked about here, called the Cosmic Explorer. This is to make the arms as long as possible, 40 kilometers. And again, it may have different components at low and high frequency. Last, let me just say that the future of gravitational wave astronomy is to cover the whole frequency band, starting from the kind of millisecond range, which is what we do in LIGO, minutes to hours, which is what will be done in space, years to decades, which is basically what's done in what are called pulsar timing, which may be the next way gravitational waves are detected, to kind of the, let's say, gravitational wave background things, which we certainly don't know how to do at present. Thanks.
Questions? You are encouraged to ask questions. It's not. Yes.
My question is, how much do we have to increase the sensitivity to see far the beginning of the universe?
Okay, I think if I understood the question is how much do we have to increase the sensitivity to see signals from the early universe?
Yes.
That's a kind of twofold answer. One is if you wanted to do it in LIGO or Virgo, the present detectors, we have a big disadvantage. We're at very, very high frequency and not at low frequency. That means that not only aren't we sensitive enough, we don't know how to predict how it'll be at our frequency range. You can take very optimistic models that include models of inflation that would give maybe detectable signals in the finite future in our frequency range. If you take classical inflation, however, I think it's undetectable in our frequency range. So if nature is kind and there's, superstrings is right or some other models that enhance it, it could be seen in our frequency range. The proper way to look is to go to lower frequency, which is closer to the signals that you need. The best, presently, if you go in space, they only go to, we cover, as I said, 10 to 1,000 to 10,000 hertz, roughly. In space, you cover 10 to the minus 2 to 10 to the minus 4 hertz. You want to go much lower than that. So the best device that we have that's actually real is not a device but a method, and that is that what's being done now, and I vaguely alluded to it, is to use the timing from pulsars to see gravitational waves. That's presently done with known pulsars, known signals. Nobody's done anything special for it, but it's limited by systematics. I don't know if anybody's talking about it here, I don't remember. But it's limited by systematics. If they can, once we can detect gravitational waves at lower frequencies, then we don't know how to do it yet, but you could anticipate that you can get to the kind of sensitivities that you could see effects of the early universe. So it's not coming out of the present or near-term experiments, maybe out of futuristic experiments at lower frequency. So it's a long-term goal.
Thank you for your presentation. I have wondering, as you told that the construction of a LIGO in India has begun, and the Kagra is operational right now, as I understood. You told us that by the way it's being constructed, we can access to the two components in the gravitational wave signal. So is these constructions are made to be able now to access to these two components or not?
Yes. First, I'd say we hope to be able to see the two components really with LIGO and Virgo in the near future, needing more data and so forth. But it requires much more data, and it requires Virgo to be sensitive enough. If you go as far around the world as India, I think, my associates can correct me, I think you don't have to worry about the orientation. You've got them different enough. So I think we will be able to decompose the two components, within the next, certainly in this coming decade, whether it's 3 years from now or 5, I don't know.
Thank you, Professor, for this talk. It was a very excellent introduction to gravitational waves. Now, when it comes to strong gravitational lensing, some people use gamma-ray burst explosions to search for reprints of gravitational lensing, because by measuring the time delay between two light signals that have the same shape, you can infer the mass of the lens. Can we search for lensed gravitational waves to estimate the mass of the lens? Is it possible?
I haven't thought about it. I don't know any of my... Anybody have a comment?
Hi, I'm not sure if Eric was going to cover this in his lecture, but I mean, the LIGO-Virgo collaboration do conduct searches for lensed events. So when we have these lovely binary black hole merger signals that Barry showed, right? We have the few nice oscillations and the merger ring down. We've seen about 90 of those so far. So in principle, it could be the case that 2 of those are actually the same event that got lensed and arrived at different times. And so we do, as a sort of one of our standard analyses of the data when we collect these black hole signals, is to do a comparison of the signals to each other to see if any are consistent with being lensed. And we have a couple of papers on that. Nothing, no positive results so far, but that's not surprising considering the fairly small number of things we've detected, only about 100, less than 100, and from the relatively nearby universe. But there are prospects in the future, and certainly I think with the next generation, we should expect to see that.
Hello.
Hi.
Before you said, talking about the future interferometers, that the purpose is to go to lower frequencies, as low as possible. Is it a difficulty to go to higher frequencies in general?
Is what? Say
Is it a difficulty to go to higher frequencies in general, in gravitational waves?
higher frequencies?
Yeah.
Yeah. First, the attempt to go to lower frequencies is obviously motivated by the black hole signals. There's motivation to try to be better at high frequencies. That real motivation that comes from the fact that if you look at for example, the merger of the neutron stars, there should be signals after the merger that are at high frequencies, and that relies on kind of nuclear physics. And so having better sensitivity at high frequencies is an aim. Right now, the present generation, we try to do everything at once. The Australians have looked at making an interferometer that will be optimized at high frequencies, and they don't worry about all these seismic problems and so forth at low frequencies. It's not funded yet, but it's certainly a concept that would emphasize high frequencies. We're probably a couple orders of magnitude away from where we'd like to be above 1,000 hertz to see the kinds of after effects that we might detect, for example. So our motivation has come from that.
Thanks.
Thank you again, Professor, for your talk. I was wondering if you could expand on what new analyses we could do or things we could learn about binary systems once we're able to resolve the 2 polarizations of the gravitational wave.
Alessandra maybe is close to what she's talking about, so maybe. I don't know if you're specifically talking about
no, I will not actually discuss this, but maybe I can add 2 things. So first, of course, if we can measure more parameters on which the waveform depend on, this is important because you can disentangle the parameter, you can measure them better. But for the polarization, something interesting is if you go beyond the theory of general relativity, there are more than 2 polarizations, and you can test them only if you have access to if you can measure all the 5. In fact, 5 are the number of possible polarization that you have if you go beyond the theory of general relativity. So having more detectors will allow actually to do this kind of test.
Yeah, let me just add to that a general problem that we have is that it needs to be part of our mission or goal to actually see if Einstein's theory of general relativity is the right theory of general relativity, or we have to go beyond that. And so this is one place where you might see differences. And now, I didn't mention it, but we do tests of general relativity, like where I put in, and saw if there was a graviton. We're limited, say, compared to my background in particle physics, where you compare different theories by seeing how well the data how well the data is described in theory A versus theory B. We're not able to do that. Because any variants of general relativity usually don't have the detailed predictions that we have in Einstein's theory. So we're not able, in the tests we're doing now, where we measure the parameters of general relativity, we can see how well we can measure them, but we can't really compare that rule out some other alternate theory very easily, because alternate theories aren't really carried to the same level. So it's a big mission, and I think in the long term, to see how well and how different real life is from Einstein's theory of general relativity. And certainly this question is one avenue, but in general we do it by just seeing how well and whether there's any deviations in Einstein's theory at present.
Okay, thank you very much. I think we will stop for a half an hour break.